Let's jump right in. Have you ever looked at a modern cargo ship, a literal Goliath of steel spanning hundreds of meters, and wondered how human beings actually put something that massive together? Well, the truth is, where a ship is built matters just as much as how it's built. In this explainer, we're looking at the birthplace of a ship. Whether it's constructed on an angled slope or entirely flat ground, these two environments represent fundamentally different production philosophies, and they dictate exactly how these giants are assembled piece by massive piece. Here's our roadmap for today's explainer. We'll cover where ships are born, the traditional slipway, the modern building dock, the economics of choice, assembling the Goliath, and finally, the critical joint. Section 1, where ships are born.
We need to start by understanding the core logistical problem here. The immense weight and size of today's commercial vessels require a highly specialized engineering solution just to house them during construction. Remember, we aren't building cars here, we're building floating cities. So I want you to ask yourself, which birthplace is actually better for a massive ship? Imagine the sheer logistics of just housing a 300-meter-long hull. The two main options available to shipbuilders represent two totally different approaches, and each comes with its own unique set of engineering hurdles.
Section 2, the traditional slipway. Let's look at the traditional method first, where gravity acts as both a helpful tool and, honestly, a constant antagonist. Notice the steep angle here. A slipway is an inclined concrete surface leading down to the water. The ship is built directly on this permanent slope, resting on keel blocks, growing upward and outward. When it's finished, the weight is transferred to a launching cradle, and the vessel literally slides down the ways into the water. Now, while the slipway is a classic, low-cost method to maintain, it comes with massive logistical headaches. Because you're building on a 1 in 20 to 1 in 40 incline, literally everything is more difficult. Your heavy equipment, your materials, and your crew must constantly operate on a slant. Plus, the sheer size of the ship you can build is strictly limited by the physical length of the slipway itself. You simply can't build a ship longer than the concrete it sits on. Section 3, the modern building dock.
So, how do we solve the slope problem? We move to the modern standard, the building dock. It's exactly what it sounds like, a dry, sealed basin with a perfectly flat floor. Think of it as a massive industrial swimming pool that's been emptied out. By building on a flat surface at ground level, block erection, crane operations, and all outfit work become dramatically easier and way safer. When the ship is complete, you simply open the dock gates, the water floods in, and the ship gently floats off its keel blocks. There's no sliding, no chain drags, no dramatic wall of spray.
This comparison is crucial. The angled slipway limits you. You're fighting gravity every single step of the way, and the launch puts immense dynamic structural loads on the hull. On the flip side, the flat building dock gives you ultimate scalability. That dry dock float-off has virtually zero dynamic loads, meaning the hull is never subjected to the immense impact and acceleration forces of a traditional slipway launch. Section 4, the economics of choice. So why would a shipyard choose one over the other? Because, as with everything in maritime engineering, it all boils down to economics. Walk through this decision tree with me. For smaller ships or yards with lower production volumes, a slipway might still be the right answer because of its low capital cost. But if you're building very large crude carriers, VLCs, or massive container ships, a flat building dock is absolutely essential. The steel blocks are simply too massive to handle safely on a slope. For yards aiming for high throughput, the huge production efficiency gain of a building dock easily outweighs the high initial cost of building the basin. In fact, many large yards operate multiple building docks at the same time. Section 5, assembling the Goliath. Okay, now that we have our chosen environment, how do we actually piece this Goliath together? Modern ships are prefabricated in blocks under covered shops, but eventually those blocks have to be brought to the dock and joined. Take a guess for a second. Where does the actual assembly of a massive ship begin? You've got a 300-meter-long vessel. Which part of this giant 3D puzzle goes down onto the keel blocks first? The erection sequence almost always starts at the aft machinery space. That's the engine room region at the back of the ship. And why? Because that is where the heaviest structural blocks are located, and it's where the main engine sits. Starting here gives the engineers the longest possible lead time to install the complex propulsion machinery and shaft lines, all while the rest of the hull continues to be built forward. Now, to speed up this erection process, modern shipyards use the marvel of the megablock. This takes prefabrication to a mind-blowing scale. A megablock is a single structural unit that spans the full beam, meaning the entire width of the ship from port to starboard.
It's essentially a massive slice of the ship pre-joined together before it ever even reaches the dock. Check out how this builds incredible efficiency. In a standard approach, a crane might have to make 150 separate lifts of 200-ton blocks, perfectly aligning each one. But with the mega block strategy, a massive gantry crane lifts a single 2,000-ton unit into place. You reduce the entire process to just 10 or 15 lifts total. That means way fewer crane lifts, fewer joints to weld, and vastly less time sitting in the dock. Section 6, the critical joint. But bringing two 2,000-ton mega blocks together creates a terrifying engineering challenge: alignment. I want you to really focus on this number: 3 millimeters. When two massive blocks of a ship meet, their structural members must align perfectly across the joint. The maximum allowable tolerance for structural misalignment is just 3 millimeters. We're literally talking about thousands of tons of steel matching up to the width of a couple of coins. How in the world do they pull that off? Highly skilled surveyors use advanced optical total stations to check the alignment. To make the tiny, precise adjustments required, they use heavy-duty hydraulic jacks to literally nudge these thousands of tons of steel into perfect position, long before a single structural weld is made. It's a slow, meticulous ballet of heavy engineering. Which brings us to a fascinating logistical hurdle. What happens when a shipyard wins a contract for a ship, but the designed hull is actually longer than their available building dock? Do they just turn down a multi-million-dollar contract? No way! They use what's called the split construction method. The hull is built in two entirely separate halves. Each section is completed, floated out of the dock, and then the two halves are brought together out in the open water. To weld them, temporary watertight boxes called cofferdams are built around the outside of the joint and pumped dry. Achieving alignment here is arguably the most demanding operation in shipbuilding because both halves are literally bobbing in the water. The target? A perfectly straight keel line within a 10-millimeter tolerance over a total length of 380 meters. It's absolutely staggering. So, the crucial takeaway from this explainer is this: the environment a ship is built in, whether it's a traditional gravity-fighting slipway or a highly controlled flat building dock, is just as critical to the process as the steel itself. Prefabricating megablocks and perfectly aligning them requires a stable, highly engineered birthplace to maximize both efficiency and safety. And that leaves us with this final thought. Ships are only getting bigger, constantly stretching the limits of our current infrastructure. So, as global trade demands ever larger floating Goliaths, what new engineering marvels will eventually have to replace the building docks of today? It's a thrilling question for the future of maritime engineering. Thanks for joining me on this deep dive into where ships are born.